Thanks. Well, welcome. I'm glad that you all could come here today and hear about all the things that I've been doing inside of black holes. So I'm going to start out by just mentioning that we have a broad audience here today, and so I want to be as pedagogical as possible in my presentation. But I also realized as I was preparing that I'm condensing 6 first author works into a single presentation, which is never a good idea. So I hope that you'll forgive me if I rush through things a bit fast, but please do feel free to stop me if there's anything that I don't really explain fully. And hopefully it's all unified under one common theme. And that theme is to answer this research question of what happens if you fall into an astronomically realistic black hole. And so to answer this, we're going to split this talk into 2 parts. The first is going to be using the framework of classical gravity. So this is using Einstein's general relativity theory that describes gravity on large scales. And you can make a bunch of predictions about geodesics and visualizations and cool stuff like that. And then the second half of the talk will focus on what quantum mechanics can tell us about gravity. So this will be under a framework called semiclassical gravity, of how gravity behaves on a quantum level, at least to first order. So the first thing I want to just get out of the way right away is the most common question that I hear asked is this actually physics? And why should we care in the first place about what happens inside black holes? I mean, by definition, black holes are things that you can't escape. You can never see anything inside of it. So are we actually predicting anything we can observe? And it turns out that you can. And so we're trying in this thesis to come up with a theory which is not just mathematical, but is also physical. We're trying to map this to realistic systems that have rotation and accretion and all these other things that we observe in astronomy. And also, when you take quantum mechanics into account, it turns out that things can escape black holes. This is what Hawking radiation is, and so we'll see exactly what that is. And usually it's too small for you to actually see from Earth or anything like that. But it can have profound implications for what you would see falling in. And this instability that we're going to talk about inside a black hole can completely change the geometry of the black hole and even change the external parameters that you might be able to observe, like the spin or the mass function. Okay, so with that, let's start out and talk about some classical physics. And the starting point is the simplest model of black hole that we have, the Schwarzschild solution. So this was a solution that was come up with by a guy named Carl Schwarzschild, the guy with the epic mustache right there. So he was trying to find a solution to Einstein's equations of general relativity that he had just come up with. And the solution that he came up with is the following, the space-time line element that you see here. So in general relativity, time and space form one unified manifold. And usually we describe that with a line element, which is nothing more than Pythagorean's theorem. So it's a way of encoding how distances are measured in your space. And so if you have just a flat space, then this would say that ds squared is dx squared plus dy squared plus dz squared. But now that we have this black hole, we see there's this extra function right here that acts in time and space in this various way. It's called the horizon function. And for the Schwarzschild black hole, it takes this form, and we can see it plotted right here. So you can think of this as a gravitational potential of sorts. So if you're starting out at some large radius, you can fall in and eventually reach the center of the black hole. And the point where this horizon function crosses 0, the root of the horizon function is the event horizon. So this is the point of no return. You can visualize a black hole also as space flowing inward, kind of like a whirlpool. And if you do that, then the horizon is the position where space starts falling faster than the speed of light. And so if you are within this position, then there's no way you can escape back out of the horizon because you can't go faster than light yourself. And so you're doomed to reach the singularity. And if you're curious, this bird did make it out okay. Okay, so these are the ways that we can visualize black holes in general. You can plot the horizon function, you can draw these animations, but usually scientists don't like drawing animations if you're publishing papers, things like that. So there's a better way of visualizing black holes that keeps track of both information about space and time. These are called Penrose diagrams. And raise your hands if you're comfortable with Penrose diagrams. Probably not a lot of you. Okay, so about roughly half of you. That's more than I expected. That's great. So let's just go through briefly what we should know from these diagrams. So they're plotting space and time. And the key thing that Penrose did was two things, actually. The first was we have an infinite space here. We want to crunch that down into a finite space. So infinity is at a finite point here on these Penrose diagrams. And the second thing is that light rays are always drawn with a slope of plus or minus 1. Plus 1 if they're going outwards, and minus 1 if they're going inwards. And so this is just a flat space-time. You can see a light ray comes in, it bounces off of the origin because we're only plotting positive radius, and then continues off like that. What would a black hole look like? Well, it would be something like this. So we have our normal universe, just like usual with infinity out here. But this light ray now, instead of going through the origin and then coming back out to infinity, is now going to reach r equals 0. And that's the end of its journey. And so any point past this line right here, which we call the event horizon, is a point of no return. Because if you are inside of this black hole, then there's no way that you can return to the universe that you came from. So this is a Schwarzschild black hole. It turns out that for quite a while, people didn't really believe that this had any physical meaning. Einstein himself, for several decades, didn't really think that this was worth studying or that it corresponded to anything in reality. And one of the reasons for that was because this is an eternal black hole. So it has existed for all time. And you can see here, there's this surface right here that is technically a white hole horizon. So if you look infinitely far into the past, there is not our normal universe you see. There's still this black hole, white hole analytic solution that you can find. So it wasn't until a few decades later that people were finally able to connect this to the physical reality that we live in. And one of those people was the father of the atomic bomb, Oppenheimer, who with his student came up with this model that has this red line right here is a collapsing shell of matter that mimics a star that might collapse to form a black hole. And so now we have this model that we can see that stars actually can form black holes, and that they do actually correspond to things that we see in the real universe. So in everything that follows, I'm not going to be using this Oppenheimer-Schneider model directly. Instead, we're going to use these eternal spacetimes, which is an appropriate choice as long as we take the collapsing star to have occurred far enough into the past and then apply the appropriate boundary conditions at that past horizon. Okay, so let us see how we can visualize this. So there's this code, the black hole flight simulator, that my advisor, Andrew Hamilton, had developed a few decades ago that is absolutely amazing. You can ray trace in real time to show you what Einstein's equations would predict you would see if you were to fall into a black hole or fly around or throw something else into it. There's a bunch of different things you can do. So we'll see exactly what happens when we fall into this Schwarzschild black hole right here. You notice there is a shadow of the black hole where light is bending around it. And we can also follow along Penrose diagram or just a slice of what it looks like in space. Right, so we're going to start out at a few hundred gravitational radii away. This is about 17 AU if we were considering the black hole at the center of our galaxy. So that is roughly the distance of the closest star that we've ever observed that has come to Sagittarius star. But that's not really as relevant. So let's just see what happens. Ah, I did optimize, and I am regretting optimizing. Okay, let's hope that this works. So we're about to cross the event horizon here. Ha, nothing special has happened. We can still see that black hole shadow in front of us that is growing over time. So let's tilt our view a little bit so we can just see that horizon in front of us, which is not the event horizon. Now we're really slowing down time. So we're in the last fraction of a second. We can see that the entire sky above us is squashing down and forming just an infinite plane and getting highly redshifted until, let's stop it right there. We basically hit the singularity. So when you reach the inside of a black hole and you land on that singularity, you don't reach a single point. The singularity is not just a single point. It's actually this infinite plane from this view that you can see in all directions. So it is a space-like singularity, which means that it's unavoidable. And no matter how you fall in, each spot you're always going to land on that singularity at some point in time. You can never steer away to avoid it. Okay, so that is a Schwarzschild black hole. It's a great solution, but we want to go beyond that. So there are a few things that we might want to do that generalizes from the Schwarzschild solution. So here is just normal spherically symmetric black hole. But in reality, black holes don't look like that. They actually might look something like this. So if you add rotation to a system, most objects in the universe have angular momentum, then that'll change what your space-time looks like. And in actuality, black holes don't just look like that. They might look something like this. So black holes are surrounded by accretion disks with highly energized plasmas and all sorts of jets and weird things that we might want to understand. And many of these people in this room are trying to simulate and understand. So I'm not going to be dealing directly with the geometries of accretion disks, but we will go through how rotation and accretion affects the interior geometry. So let's start with rotation. The simplest model for a rotating black hole was first developed in 1963 by Roy Kerr, and he found this line element. It's a bit more complicated, but we can see some of the same structures. So there's a horizon function here that looks like this. And so the main difference in this horizon function, so there's this parameter A that measures the spin of the black hole. And now there's not only one horizon, but there's actually a second horizon where the root of this horizon function. And this we're going to call the inner horizon. It also gets called the Cauchy horizon. And you can think of this, if you're picturing space as flowing inward, the event horizon or the outer horizon is where it starts flowing faster than light. The inner horizon is where it once again slows down to slower than the speed of light. You could think of this as the rotation of the space-time is causing a centrifugal force that's flinging you outward. So you can't actually reach to the very center. And the point at which you're prevented from doing that, where you start to slow down slower than light again, is this inner horizon. You can also draw a Penrose diagram, and we can see a bit more structure that we'll analyze in a bit. So there's a universe, black hole, and then the inner horizon gets split into these two sections here. And beyond it, you can see that our origin, r equals 0, is now no longer space-like, but it's now time-like. So this is something that you can avoid. You can just steer around it. But then the question is, what happens beyond that? We have a singularity, and so the equations break down. So we might want to know what that is. Okay, so yeah, just once again, there's the event horizon, and there's the inner horizon.